What's up everyone? Another batch from Stack Lessons, 20 questions on retrieval strategy, MLflow Model Lifecycle, and AI Gateway Guardrails. Format is the same: question, countdown, reveal, explanation. 10 seconds is the timer. Strap in. Alright, question 1. Choose for this case, not every case. A generative AI engineer is building an assistant for a financial operations team that answers questions about transaction history, current account balances, and monthly spending summaries. This data resides in structured delta tables with defined schemas. The engineer is deciding whether to embed the data into a vector store or use a different retrieval approach. Which strategy is most appropriate for this structured tabular financial data? Select one. Review the answer choices on screen. The correct answer is option D. Semantic similarity cannot match an exact dollar figure. Structured tabular data containing precise numerical values and relational information is best retrieved through SQL queries rather than vector similarity search. A SQL query tool integrated into the RAG pipeline enables the LLM to generate and execute queries that return exact values for account balances, filtered transaction records, and aggregated spending summaries, results that semantic search cannot reliably produce. Embedding table rows as text chunks introduces a lossy conversion that makes numerical comparisons unreliable and discards the column-level structure that SQL can leverage precisely. Converting rows to natural language descriptions with semantic chunking adds processing overhead without resolving the fundamental mismatch between embedding-based retrieval and exact structured lookups. Feature serving is designed for delivering real-time ML features to inference endpoints, not for supporting ad hoc queries over historical financial records. Alright, question 2. Look for the limiting phrase. A generative AI engineer at Woodgrove AI has spent several weeks iterating on a summarization model using MLflow 3, logging faithfulness scores, NDCG values, and latency measurements as part of a logged model across dozens of runs. After identifying the best performing run, the team wants all captured performance data from the development phase to appear directly on the model's registry page, so that a review committee can assess the full history without navigating individual experiment runs. What should the engineer do? Select one. Review the answer choices on screen. The correct answer is option D. All three alternatives break traceability in different ways. When a logged model is promoted to a Unity Catalog model version, all metrics, parameters, and traces that were recorded during the development phase automatically surface on the Unity Catalog model version page, giving reviewers a single governed location with complete performance history. Exporting metrics to a CSV and attaching it as an artifact is entirely manual, is not integrated into the registry interface, and is not queryable alongside model metadata. Re-logging every metric under a new run duplicates data, detaches measurements from their original experimental context, and adds unnecessary maintenance overhead. Copying metadata to a separate delta table requires building custom tooling and access controls outside the registry, removing the traceability that Unity Catalog model versioning provides natively. Here we go. Question 3. Pay attention to what is really asked. A generative AI engineer at Contesso Health is integrating a patient appointment scheduling assistant with a foundation model endpoint through AI Gateway. Patient messages may contain social security numbers, email addresses, and phone numbers. Compliance policy requires that PII is never transmitted to or from the underlying model. However, the system must attempt to process every incoming request rather than reject it when PII is detected. Which AI Gateway feature should the engineer configure? Select one. Review the answer choices on screen. The correct answer is option C. One word separates redaction from rejection in the spec. PII detection and redaction allows requests to proceed by substituting detected personal information, such as social security numbers, email addresses, and phone numbers with placeholder tokens before the payload reaches the model and before the response is returned to the caller. This satisfies both the compliance requirement that PII is never transmitted and the operational requirement that every request be served. Safety filtering targets content categories such as hate speech, violence, and sexually explicit material. It does not detect or redact structured PII fields like identification numbers or contact information. Rate limiting controls how frequently requests may be submitted to protect SLA and prevent cost overruns. It does not inspect or modify the content of individual requests. PII blocking rejects the entire request whenever personal information is detected, which directly contradicts the requirement to process every request. Here we go. Question 4. Look for the answer that fully satisfies it. A generative AI engineer at Ironside Financial is using hybrid search in Databricks AI Search to retrieve investment research documents. Verbose reports containing extensive keyword repetition consistently outrank concise, highly relevant documents even though the focus documents are more useful. The engineer wants to reduce the scoring advantage gained from keyword repetition without changing how document length influences scores. Which configuration change should they make? Select one. Review the answer choices on screen. The correct answer is option D. Lowering K1 makes saturation arrive sooner, not later. The K1 parameter in BM25 controls term frequency saturation, the rate at which additional occurrences of a keyword stop, contributing meaningfully to a document's relevance score. Decreasing K1 makes saturation kick in sooner, so the 100th occurrence of a keyword contributes negligible additional score compared to the first few occurrences. This directly resolves the problem of keyword-dense reports dominating results through repetition. Increasing K1 raises the saturation ceiling, making each additional keyword occurrence more impactful and worsening the existing bias toward verbose reports. The B parameter governs document length normalization rather than term frequency behavior. Decreasing B reduces the penalty on longer documents, amplifying rather than reducing their scoring advantage. Increasing B penalizes longer documents more broadly, but does not specifically address how keyword repetition accumulates score, and the engineer explicitly wants to leave length normalization unchanged. Let's slow down here. BM25 has two knobs, and the exam tests whether you know which does what. Imagine you're a judge at an essay contest. One student writes justice 50 times. Should all that repetition beat a focused argument? That's the K1 problem in BM25. The K1 parameter controls how quickly extra keyword hits stop adding score. A high K1 means the 50th occurrence still earns nearly as much as the first. A low K1 means saturation hits fast. After 5 occurrences, more hits barely register. The B parameter is different. It controls the length penalty. The question says leave length alone, so B is off the table. You only need to kill the repetition advantage, decrease K1, and you cap what repetition can earn. That's why D wins. Next up, question 5. Underline the key phrase mentally. A generative AI engineer is evaluating 2 fine-tuned versions of an enterprise knowledge assistant using 300 held-out questions. The goal is to determine which model produces responses that users will prefer, rather than whether either model passes a fixed quality threshold. Which evaluation method is most appropriate? Select one. Review the answer choices on screen. The correct answer is option B. Relative preference, not a pass-fail threshold, drives the method. Pairwise comparison is the appropriate method when the objective is to determine which of 2 models produces relatively better outputs, not whether either clears an absolute quality bar. Presenting responses side by side to a judge, whether an LLM or a human reviewer, captures comparative preference directly, which is what user satisfaction studies measure and what head-to-head deployment decisions require. Single output scoring assigns an absolute numeric grade per response, which is useful for pass/fail deployment gates, with a defined threshold, but does not directly answer which of two models is preferred relative to the other. Precision at K is a retrieval metric that measures how many retrieved chunks are relevant, not a method for comparing the quality of generated text between two model versions. G-eval produces a structured absolute score per response, which again measures individual quality rather than comparative preference between candidates. 5 in SQL consistently wins when data is structured and exact. PII redaction in AI Gateway is distinct from blocking, and the logged model to UC path keeps all metrics alive without manual work. Here we go. Question 6. Read it carefully. Quick check. A generative AI engineer at Paramount Analytics is building a content policy enforcement platform for a media sharing service. Each submission includes a thumbnail image and an attached video clip. The platform must analyze both the image and the video in a single model call to detect policy violations and return a structured classification. Which foundation model API model natively supports this requirement? Select one. Review the answer choices on screen. The correct answer is option D. Native video support narrows this to a single candidate. Gemini 2.5 Flash natively supports all 4 input modalities: text, image, video, and audio, through the Foundation Model API. This native video support is the decisive differentiator that allows a single model call to process both thumbnail images and video clips without any additional pre-processing pipeline. Claude Sonnet 4 supports text and image inputs within the Foundation Model API, but does not support video as an input modality, making it incapable of natively ingesting video clips for policy analysis. Llama 4 Maverick similarly supports text and image inputs only, and cannot process video content without a separate frame extraction step that reroutes the workload outside the model's native capabilities. BGE Large is an embedding model that produces vector representations for retrieval and similarity search. It cannot interpret visual or video content, cannot detect policy violations, and cannot generate structured text output of any kind. Now, question 7. Do not reward the familiar term. A generative AI engineer has configured an inference table with a sampling fraction of 1.0 to capture all requests to a document processing endpoint. During an audit, the team discovers that certain large document submissions and a subset of error responses are absent from the inference table even though the endpoint processed them. What are the 2 most likely causes of the missing entries? Select 2. Review the answer choices on screen. The correct answers are option B and option D. 2 separate documented limits each silence a different subset. 2 distinct documented limitations explain the selective gaps. Inference tables do not log payloads that exceed 10 MB per request. Large document submissions that breach this threshold are silently excluded while smaller requests continue to be captured normally. Additionally, requests that result in 401, 403, 429, or 500 status codes may not be logged, so a subset of error responses will be absent from the table even when the endpoint handled them. Multiple replicas do not affect inference table coverage because logging is applied at the endpoint level regardless of how many instances serve traffic. Inference tables are supported for both pay-per-token and provision throughput endpoints, so the serving mode is not a factor. A schema change to the inference table stops all subsequent logging entirely rather than creating selective gaps. If this had occurred, no records would appear after the change, which contradicts the observation that most requests are present and only specific entries are missing. Let's slow down here. Inference tables have two silent blind spots the exam loves to test. Imagine you set sampling fraction to 1.0 and expect every request to land in the table. It doesn't. Think of it like a net with two kinds of holes built in. First hole. Payloads over 10 MB get silently dropped. Send a 12 MB document batch and the table never records it. Second hole. Certain error codes, 401, 403, 429, and 500, may also go missing. The table works with all endpoint types, pay per token included. Here's the distractor trap. A schema change kills MLflow logging at once. You'd see 0 new rows after that, not a selective gap. So when only specific entries are absent, blame two silent drop rules, not a broken config. Let us keep moving. Question 8 starts now. A generative AI engineer at Alpine Diagnostics is running fine-tuning experiments for a medical summarization model. Each experiment produces model artifacts approximately 4.7 gigabytes in size. The team requires that artifacts be accessible from multiple Databricks workspaces and be subject to Unity Catalog access controls and lineage tracking. Where should the engineer store these MLflow artifacts to meet all three requirements? Select one. Review the answer choices on screen. The correct answer is option D. All three requirements resolve to one governed storage layer. Unity Catalog volumes provide file-level storage governed by Unity Catalog, supporting access controls, lineage tracking, and cross-workspace accessibility. All three requirements stated by the team. Artifacts logged to Unity Catalog volumes are subject to the same Unity Catalog privilege model as tables and models, enabling consistent governance across the organization. The per-artifact file size limit of 5 GB accommodates the 4.7 GB artifacts without issue. DBFS is the default MLflow artifact location but is workspace scoped, meaning artifacts are not directly accessible from other workspaces and are not subject to Unity Catalog access controls or lineage. An external S3 bucket accessed using Databricks secrets bypasses Unity Catalog governance entirely. Access control and lineage tracking would need to be managed outside the UC framework. A Unity Catalog Delta table is designed for structured tabular data, not for storing large binary model artifacts, and cannot accommodate files approaching 5 GB as Delta records. Let us keep moving. Slow down for question 9. A generative AI engineer at Northwind Analytics is fine-tuning a text classification model and needs to record 3 pieces of information in MLflow: the learning rate chosen before training begins, the training accuracy captured after each epoch, and a string label identifying the experiment owner. Which combination of MLflow API calls correctly handles all 3 requirements? Select one. Review the answer choices on screen. The correct answer is option B. Static config, sequential measurement, annotation, each has its own API. MLflow organizes run metadata into 3 distinct categories based on nature and mutability. Parameters capture static configuration values fixed before training begins. Learning rate and other hyperparameters are canonical examples and are recorded using MLflow.log_param. Once written, a parameter value is immutable, which reflects that it represents a fixed input to a run rather than an evolving measurement. Metrics capture numeric values that change as a run progresses and accept an optional step index, making per-epoch training accuracy a natural fit for MLflow.log_metric, with a step argument. This produces a step-indexed time series that MLflow renders as a training curve and enables meaningful cross-run comparison. Tags are free-form string key-value pairs used to attach contextual annotations such as owner identifiers, dataset provenance labels, or experiment purposes, and are set with MLflow.set_tag. Swapping parameters and metrics inverts their semantics, Treating learning rate as a time-varying quantity and training accuracy as a static preset destroys the step-indexed history and makes cross-run comparison incoherent. Storing training accuracy as an artifact via MLflow.log_artifact writes numeric values as opaque file blobs, rather than structured, queryable metric data, eliminating the step index and the ability to visualize training curves. Using MLflow.set_tag for learning rate stores it as an untyped string annotation rather than a typed, filterable parameter, breaking hyperparameter-based run filtering and comparison. Let's slow down on this one. MLflow has 3 different logging calls and it matters which you pick. Imagine you're training a text classifier at Northwind Analytics and need to log 3 things in MLflow. Here's the mental model. A learning rate is fixed before training starts, it never changes, so it's a param. Training accuracy shifts every epoch. You want to watch it change. Use a metric with a step argument that builds a curve you can actually graph. The experiment owner is just a string label, a tag. The trap is answer A log_artifact saves a file blob, not a queryable number. You lose the chart entirely. Answer B gets all 3 right. Let us keep moving. Question 10. Let the constraints drive the choice. A generative AI engineer at Goldfield Analytics is evaluating the retrieval quality of a customer support RAG system. Articles in the knowledge base vary in relevance. Some are highly useful, others only partially helpful, and the UI prominently surfaces the top-ranked result, so ranking position matters significantly. The engineer needs metrics that capture both graded relevance intensity and document ranking position. Which 2 metrics satisfy these requirements? Select 2. Review the answer choices on screen. The correct answers are option B and option D. Graded relevance and position sensitivity must both be present. DCG at 10 and NDCG at K both satisfy the 2 requirements. DCG at 10 assigns each retrieved document a relevance grade between 0 and 3 and applies a logarithmic discount so that highly relevant documents ranked lower contribute less to the overall score than equivalent documents ranked first, directly encoding both intensity and position. NDCG at K divides DCG by the maximum possible DCG score, normalizing it to the 0 to 1 range, and enabling fair comparison across queries with different numbers of relevant documents while retaining the same graded relevance and position sensitivity. Recall at K counts how many relevant documents appeared in the top K results, but treats all retrieved positions equally and assigns only binary relevance, capturing completeness but neither graded intensity nor ranking order. Precision at K measures the proportion of retrieved documents that are relevant without regard to their order within the result list. F1 at K balances precision and recall at a threshold but uses binary relevance judgments and does not account for document ranking position. This one trips people up. Let's look at what position sensitivity actually means in numbers. Imagine your RAG system returns a highly relevant article at rank 5 instead of rank 1. Does that hurt your score? It depends on the metric. DCG, discounted cumulative gain, multiplies each result's relevance grade by a position weight. Rank 1 gets full weight, 1.0. Rank 2 drops to 0.63. Rank 3 is already at 0.5. Rank 10 falls to just 0.29. A grade 3 article buried at rank 10 is worth less than a mediocre one at the top. NDCG normalizes that score to 0 to 1, so you can compare queries fairly. Recall at K and precision at K skip this position discount entirely. For those metrics, rank 2 counts the same as rank 1. The question demands both graded relevance and position sensitivity. Only DCG and NDCG deliver both. That's the trap. BM25's K1 controls term frequency saturation, B controls length normalization. Inference tables cap payloads at 10 MB silently. For graded relevance with position sensitivity, only DCG and NDCG qualify. Time for another one. Question 11. Translate the story into requirements. A legal research firm stores thousands of case documents in an AI search index. Attorneys frequently search using exact statutory references such as 42 U.S.C. Section 1983 and contract clause identifiers. Pure vector similarity search often fails to surface documents containing these exact citations, because embedding models treat legally distinct identifiers as semantically similar. Which search configuration best addresses this retrieval gap? Select one. Review the answer choices on screen. The correct answer is option B. Statutory identifiers sit outside semantic similarity's reliable range. Hybrid search combines dense vector similarity with BM25 keyword search. BM25 is specifically effective for exact term frequency matching, making it well suited for statutory references and clause identifiers where lexical precision is critical. Vector similarity complements this by capturing semantic relationships between related legal concepts. Together, hybrid search surfaces documents matching either exact terms or semantic intent, directly closing the gap that pure vector retrieval leaves for precise identifiers. Semantic chunking improves boundary placement, but does not change the retrieval algorithm or add lexical matching for exact citations. Increasing embedding dimension adds cost and latency without specifically improving the model's ability to distinguish legally distinct identifiers that share similar semantic neighborhoods. Direct access indexes change who manages embeddings, not the retrieval mechanism, and do not add keyword-based search capabilities. Time for another one. Question 12 is up. A generative AI engineer at Stockton AI has built a document pre-processing pipeline using a custom NLP library. The pipeline wraps a set of text transformation functions in a Python class with a predict method. They want to deploy this pipeline as a model serving endpoint so other teams can invoke it via REST API. Which approach correctly packages and deploys this custom Python model? Select one. Review the answer choices on screen. The correct answer is option A. Any custom Python class deploys through exactly one wrapper. MLflow Python function is the standard mechanism for packaging arbitrary Python logic as a deployable model. By subclassing MLflow.pyfunc.python model and implementing the predict method, the engineer encapsulates the custom NLP pipeline in a format that MLflow can log with dependency information, version in Unity catalog, and serve through a model serving endpoint accessible via REST API. Using MLflow.sklearn.log_model requires the model object to conform to the scikit-learn estimator or transformer API internally. A custom NLP class built on a different library does not satisfy this requirement even if it exposes a predict method. AI Gateway with external model registration is designed for routing requests to already deployed remote services, not for deploying Python classes that exist only locally. Feature-serving endpoints are purpose-built for delivering pre-computed or on-demand feature values to inference pipelines. They are not a general-purpose model deployment surface for custom NLP logic. Time for another one. Let's check question 13. A generative AI engineer at a Datum Corp has trained several iterations of a summarization model and wants to follow a structured lifecycle from development to production. The team needs performance data from training runs to remain accessible once the model enters production, and the governance team requires lineage tracking and access control on the promoted artifact. Which approach should the engineer use? Select one. Review the answer choices on screen. The correct answer is option D. Promotion is automatic, no relogging, no manual transfer. Registering a model as an MLflow logged model automatically captures metrics, parameters, and traces throughout the development phase. When the logged model is promoted to a Unity Catalog model version, all performance data becomes visible on the UC model version page, providing full continuity without manual re-entry. Unity Catalog natively enforces lineage tracking and access controls at the catalog, schema, and object level, satisfying the governance requirements without additional configuration. Storing checkpoints in DBFS without a registry loses the structured experiment history and provides no access control or lineage integration. Creating a separate experiment and relogging metrics manually introduces transcription errors and breaks the traceable link between development runs and the deployed artifact. Exporting to a volume with a spreadsheet for performance records is entirely manual and has no governance integration with Unity Catalog. Let us switch gears. Question 14. The wrong answers are close. A generative AI engineer at Millstream Retail is building a real-time recommendation feature serving endpoint. The endpoint must retrieve pre-materialized user affinity scores from an online feature table and apply a real-time discount calculation based on a customer's current loyalty tier. Which two feature spec components should the engineer configure? Select 2. Review the answer choices on screen. The correct answers are option A and option B. Only 2 feature spec component names are real in the SDK. Feature lookup retrieves specific columns from a feature table that has been published to the online store, making it the correct component for pulling pre-materialized user affinity scores at serving time. Feature function applies a Python UDF or transformation at inference time to compute derived values from input keys, making it the right component for the real-time discount calculation that depends on the customer's current loyalty tier. Feature pipeline is not a feature spec component. Feature pipelines are separate Databricks constructs for computing and writing features to the feature store. Feature store describes the storage and metadata layer and is not a component within a feature spec configuration. Feature endpoint is not a feature spec component. The serving endpoint itself is created separately from the feature spec that defines which features to look up and compute. Let us switch gears. Question 15. This is a distractor check. A healthcare startup is deploying a patient triage assistant through a Databricks AI gateway endpoint. Compliance requirements specify that patient identifiers such as SSNs, email addresses, and phone numbers must never appear verbatim in outgoing responses, but the response should still be delivered with those values replaced by safe placeholders. Additionally, any response containing violent language must be completely blocked before reaching the user. Which 2 AI gateway guardrail configurations should the engineer enable? Select 2. Review the answer choices on screen. The correct answers are option B and option C. Blocking rejects the response. Redaction keeps it clinically useful. PII detection with redaction on responses scans outgoing content and replaces identified patient identifiers, SSNs, email addresses, phone numbers, with placeholder tokens before the response reaches the user. This satisfies the compliance requirement of no verbatim identifiers while preserving the clinical content for usefulness. Safety filtering for violence on responses intercepts and blocks the complete response when violent language is detected, directly meeting the second requirement. PII blocking would reject the entire response whenever any identifier is found, making the triage assistant non-functional for legitimate clinical content that references patient categories or contexts. The requirement specifically calls for replacement with placeholders, not rejection of the whole response. Rate limiting controls throughput and cost but provides no data protection or content safety guardrails. Traffic splitting routes queries between model versions for gradual rollout, and does not apply content-level guardrails to individual responses. Hybrid search closes the lexical gap pure vectors leave. Feature spec uses only 2 real components. lookup, and function. Both AI gateway guardrails must be enabled separately: PII redaction for identifiers, safety filtering for violations. Keep your focus here. Let's read question 16. A legal technology company at Conteso is building a semantic search system over a corpus of 2 billion legal documents. After configuring a standard AI search endpoint, the team discovers it cannot accommodate the full document volume. Which AI search configuration should they migrate to? Select one. Review the answer choices on screen. The correct answer is option B. Crossing 1 billion vectors triggers exactly one upgrade path. Storage-optimized AI search endpoints are specifically designed for very large vector stores, supporting more than 1 billion vectors with 10 to 20 times faster indexing compared to standard endpoints. Standard endpoints support approximately 320 million vectors at 768 dimensions and cannot accommodate a 2 billion document corpus. Distributing indexes across multiple standard endpoints adds operational complexity, while each endpoint remains individually constrained by the same capacity ceiling. Switching from Delta Sync to direct access changes how embeddings are managed by the caller, but does not change the underlying vector capacity of a standard endpoint. Reducing embedding dimensions degrades retrieval quality and is not the appropriate response to a scale limitation. Keep your focus here. Question 17. Do the logic before the recall. A generative AI engineer at Redstone Insurance is deploying a customer-facing claims summarization service. The service handles predictable business hours traffic of approximately 2,000 concurrent users but drops to near zero overnight. The SLA requires sub-2-second response times during peak hours, and the budget team requires predictable monthly costs. The engineer is configuring a provisioned throughput endpoint. Which two parameters must they specify when creating the endpoint? Select 2. Review the answer choices on screen. The correct answers are option B and option D. 2 parameters are required. 3 of the options are invented. Provisioned throughput endpoints on Databricks require specifying both min_provisioned_ throughput and max_provisioned_ throughput, expressed in model units representing tokens per second. These 2 parameters define the scaling floor and ceiling of dedicated reserved compute capacity, guaranteeing consistent sub-2-second latency during peak hours, while keeping costs within a predictable fixed range. Max_tokens_per_request controls the maximum payload size for individual requests, and is not a provisioned throughput allocation parameter. Idle_scale_down_minutes does not exist as a provisioned throughput configuration field. The endpoint holds at least the minimum provisioned capacity at all times regardless of traffic. Token_budget_monthly is not a model serving endpoint configuration parameter in Databricks, and is not used to govern spending at the endpoint level. Let's slow down here. Provisioned throughput has 2 required fields, and this question is designed to make you pick the wrong ones. Think of provisioned throughput like booking a hotel room block. You reserve a minimum and a maximum. You pay for that reserved block whether guests show up or not. Drops to near zero overnight sounds like you'd want an idle scale down timer. But say you set a minimum of 3 model units. Those units stay reserved even at 3 AM. Predictable monthly costs. Sounds like you need a budget field, but token_budget_monthly doesn't exist as an endpoint parameter. Cost control comes from your min and max capacity settings. The 2 required fields are min_provisioned_throughput and max_provisioned_throughput, measured in model units. Max_tokens_per_request controls individual payload size, not reserved capacity. The word must is the signal. Find the required API fields, ignore the plausible sounding extras. Alright, question 18. Identify the business need first. A retail company is building a RAG application to help customers find products. The knowledge base includes unstructured product descriptions in an AI search vector index and a structured pricing table in a delta table with SKU, price, size, and color columns. When a customer asks what is the current price of the blue hiking boot in size 10, the system needs to return an exact price. What is the most appropriate retrieval approach for the pricing data? Select one. Review the answer choices on screen. The correct answer is option D. An exact price is a query result, not a similarity score. Structured data containing exact values like prices requires precise lookup, not approximate semantic similarity. SQL-based retrieval on the delta table guarantees exact matches on attributes like size and color, without the risk of false matches that vector similarity can introduce when numerically or categorically similar rows exist. This approach applies the retrieval method best suited to each data type, using vector search for unstructured descriptions and SQL for structured tables. Embedding pricing rows as text and using vector similarity can return near-miss results for approximate queries, but is unreliable for exact value lookups where a slight phrasing variation could return the wrong price. Summarizing the entire catalog into a system prompt would exceed context length limits for large inventories and forces the LLM to parse exact values from natural language, introducing error. Recursive character splitting destroys the row-column structure of tabular data, making individual price values unaddressable as standalone retrievable units. Alright, question 19. Ignore details that do not change the decision. A generative AI engineer at a logistics company is building a RAG application that answers questions for operations staff. The application draws from two sources: shipping regulation documents stored as PDFs, and a live package tracking database containing current shipment statuses and estimated delivery times stored in a relational table. How should the retrieval layer be designed to handle both data sources appropriately? Select one. Review the answer choices on screen. The correct answer is option C. Unstructured PDFs and live relational tables need different retrieval lanes. Structured and unstructured data are best retrieved through their natural interfaces. PDF shipping regulation documents are unstructured text that benefits from semantic similarity search in AI search, allowing the system to find relevant regulatory sections even when a staff member's query uses different terminology. The package tracking database is structured data with well-defined columns and time-sensitive values, making SQL queries the appropriate mechanism for precise lookups of current statuses and delivery estimates. Converting relational rows to unstructured text for embedding discards the precision and queryability of the relational schema and introduces embedding overhead for data that is already efficiently queryable by column. Unifying all data in a single AI search index forces structured database records through an embedding pipeline that adds latency, cost, and imprecision compared to direct SQL access. Storing database rows as JSON strings in a vector index similarly sacrifices structured query precision, while adding complexity with no retrieval quality benefit. Alright, this is question 20. A generative AI engineer is building an automated financial report analyzer for an investment bank. The application must interpret income statements and balance sheets containing complex numerical tables, compute financial ratios such as debt to equity and return on equity, and produce written summaries of each company's financial health. Both numerical accuracy and narrative quality are critical. Which model type is the best fit when quality is the primary objective? Select one. Review the answer choices on screen. The correct answer is option D. BGE Large is an embedder. It cannot compute or narrate. Financial report analysis requires a model with strong numerical reasoning to accurately interpret tabular data and compute ratios, combined with the ability to generate clear narrative summaries of financial health. Models purpose-built for numerical reasoning and financial analysis, such as GPT-5.4, are specifically optimized for this combination of capabilities and deliver the highest quality on this task. BGE Large is an embedding model that produces fixed-dimensional vector representations for retrieval tasks. It cannot perform calculations, generate text, or produce summaries of any kind. Code Llama 34B is specialized for code generation and software logic, not for interpreting balance sheets or computing financial ratios from prose and tabular data. Gemini 3.5 Flash is a multimodal model suited for vision tasks. While financial reports may contain charts, the core challenge here is numerical computation and narrative synthesis rather than image understanding. 3 takeaways from this session. First, structured tabular data with exact values demands SQL retrieval, not embedding-based semantic search. Second, promoting an MLflow logged model to a UC model version transfers all metrics, parameters, and traces automatically. Third, in BM25, K1 governs term frequency saturation and B governs length normalization. Swapping them inverts the intended effect. The rule runs through every question here. Match the retrieval method to the data type, SQL for exact values, vectors for meaning, hybrid when both matter. Lock that principle in and keep going. The patterns stack.